Okay, good morning, everyone. How was the first homework? Did you enjoy the problems? Okay, so I will look at your solutions and I will select some of the good solutions and I will post those on the course webpage. You can check that out. And the second homework is now available, so you can look at that later. And the due is, of course, next Friday. So today we will learn generating functions. So these are very, very important tools in many areas in mathematics, especially in combinatorics. So basic theory. 그러네요. Thank you very much. I didn't know that. So the generating function, we talked about this last time, just a little bit, but we will learn more fundamental things about generating functions. So generating functions are nothing but just one way of recording a sequence. But what's nice about this generating function is that we can do some kind of operations on generating functions. And when we do this, we can use theories in analysis, something like that. So let's look at the definition first. Generating functions. So let's say K is a field, but we will be mostly dealing with this C, complex, the field of complex numbers. So you can just think of K as the set of all complex numbers. So it's going to be a field. And K bracket X is the ring of polynomials in X. So X is a variable, just a formal variable, and polynomial means over K, meaning coefficients are in the field K. So, for example, elements say of K bracket X are of this form, of the form A0 plus A1x plus A2x squared plus ... ANXN, where each AI is in the field K. So this is a polynomial in X, and we say the degree is n. And the coefficients are K. That's where we use K over here. And this is, as a set, is just a set of all elements of this form. But I wrote here is a ring. So the ring means we have two operations, addition and multiplication. And addition is defined in the usual sense. This and fx times g of x, these are defined in the usual sense, usual way. Okay? So when we have two polynomials, we know how to add them. and then we know how to multiply them. So you are all familiar with these polynomials, right? Now the main object in this today's lecture, or the first lecture, is this k. Now we use two brackets like this, and this is going to be another object which is bigger than this. This is the ring of formal power series. Power series. Of course, in variable x over k. So typically, the elements can be written in this way. So it is. You can think of this as a generalization of this. Only we have infinitely many terms. A0, A1, x, A2, x squared. So we have infinite, it just never ends, where AI are elements in K. Okay. All right? So you can go forever. All right. So now, again, I said it's a ring. So we have to define two operations, addition and multiplication. So first of all, note, maybe I have to define first. So we can write this using summation, n from 0 to infinity, a sub n x to the n. Okay? So this is the same as this, just another way of writing this. Suppose we have two formal power series, like this, bn, xn. Then we have to define two operations, addition, multiplication. And addition is quite straightforward. So this is going to be another formal power series defined in this way. an plus bn xn. So you just add terms of with the same same monomial, same xn. You collect xn together and then you add their coefficients and you get another formal power series like this. And what about the multiplication? F of x, g of x. Again, because we want this to be a formal power series, we should be able to write this in this form, x to the n, with something coefficient over here, right? And here is defined like this. I from 0 to n, a sub I, p sub n minus I. Okay? So this is the definition. And if you compare this with the original or the ordinary case, I mean polynomial case, these are their generalizations, right? Addition. When we add two polynomials, we add something like this. So just imagine we have just finite terms here. Again, this may look a bit complicated, but if you think about how you multiply two polynomials, this is exactly how we multiply two polynomials. You just select one term in each factor and then combine them. All right? Any question? Do you need some examples? And we will see some example. So note K polynomial ring is a subset of the formal power series ring, right? We can think of this as a formal power series. For instance, say let's use just a specific example, like 1 plus x squared minus 2x squared. Let's say something like this. This is an element in a polynomial ring, and by identifying this with the formal power series, 0x cubed, if you identify something like this, they are all zeros after this. Then this is going to be an element here, so we can embed this inside this ring. Okay. And in combinatorics, there are several ways to write the coefficient. Usually, the recall an xn, bn xn, these are multiplied like this. But sometimes we want to use another form called exponential generating function. So let's use this definition. So when we have a sequence, infinite sequence, let's say this. The generating function, or ordinary generating function, for this sequence is just this. The formal power series whose coefficients are like this. Actually, this index is not important, so you can use I or N, anything like that. And the exponential generating function for this sequence is pretty much the same, except we have 1 over I factorial multiplied there. And sometimes this is easier to understand or study this sequence, or sometimes this generating function is more suitable for studying this sequence. So sometimes we will use this or this. Okay, I think I made a parenthesis in the wrong position. So sometimes, ordinary generative function, this can be omitted. So we just say, so generating function for this is this. And the exponential generating function for this is defined to be this. All right? And here is a proposition. When we multiply two exponential generating functions, we have, okay. If I write this means exactly the same as this. Okay. I is greater than or equal to 0. Sometimes I'm gonna use this, or sometimes this. They mean the same thing. an xn n factorial, bn xn n factorial. This can be multiplied in this way. Again, here we have x to the n generating function, exponential generating function. The coefficient is going to be like this. N choose I, f I, g, n minus I. Okay. Proof is quite straightforward, so I'll just leave it to you. Oh, thank you. Yeah. This is true. Okay, let me rewrite this. ai bn minus I x to the n over n factorial. Okay. Any question about this? Okay. So far, easy. And we have many simple properties, like for fg in formal power series, we have this property g plus f times g equals g times f times, you have one more, g plus h is equal to fg plus fh, things like that. Okay, now, so this is a ring, so it has inverse for addition, but may not have inverse for multiplication. So sometimes when we have the inverse, then we write something like this. For f of x and g of x, both in this formal power series. For this, if f of x times g of x equals 1, then g of x is called the inverse of f of x, and denoted g of x equals f of x inverse. Yeah. Or we will write this in this way, 1 over f of x. This is just a notation. For now, this is just a notation. You can write either this or this, right? An example. This is one of the most famous series, I think. Easy but very important. Geometric series. This can be proved using just these our definitions. What does this mean? Let's prove this. Let's see. What's the meaning of this? You have to understand the meaning. That's right. So this means this is the inverse or multiplicative inverse of 1 minus x. This means this is equivalent to saying that 1 plus x squared plus dot 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 1 minus x equals 1. Because this is the definition of the inverse. So all we need to show is that, this equation. If you can show that this equation is true, then we are done. How can we show an equation like this? What does this mean? By the way, 1 is also a formal power series. We will think of this as a formal power series, which is 1 plus 0x plus 0x squared plus dot dot dot, right? So in order to show this, we have to find the coefficient of x to the n. So the coefficient what is this? What I mean by this is the following. The coefficient means because this is a formal power series, right? This is a formal power series, if you multiply them, we should get a formal power series. So suppose we expand this as a formal power series like this. So the coefficient of x to the n in this formal power series means just an. So what is an? You can compute an. How? Okay, so just imagine you expand this. How do you expand this to a product of two formal power series? You select one term here and multiply them. So actually there are two cases. If n equals 0, what happens? In order to get a constant term without any x, you have to choose x. 1 here, you have to choose 1 over here. So it's going to be 1. Because this is the only way you get x to the constant term. Otherwise, here you have two choices. You can choose either 1 or minus x. What happens if you choose 1? If you choose 1 over here, you have to choose x to the n. Okay. Or if you choose this, you have to choose, in order to get x to the n, you have to choose minus x to the n. So this is going to be 0, so if n is greater than 0. That means an is 1 or 0, 1 if and only if n equals 0. That is exactly the same as this. Okay? Does this make sense to you? Actually, I didn't really use the definition. I used another technique to do this. But if you really, really want to be very, very formal, you can prove this in this way. So let me prove this in this way. the way I proved this, very formal proof, The previous proof is also a proof, but if you are a little confused, you can think about this this way. I'm doing this because this is the first time we use generating function. Later on, we will use this very quickly. All right, so let's say let an okay, and 1 minus x. We can do this, right? What is an here then? An is always 1 for every n. What is bn? No. Right, so instead of saying like this, b0 equals 1, b1 equals minus 1, and bn equals 0 for n greater than or equal to 2. Okay? Right? Fine. And let's take the product of them. N greater than or equal to 0, bn xn. What is this? Summation. Let's for now express this way. This should be another generating function. Cn is equal to, by definition, ai bn minus I. Okay? Let's compute Cn. So case 1, we will divide two cases. C0, let's compute C0. By definition, 0 ai bn minus 0 minus I. Right? But we have only one sum n over here, I equals 0. So a0, b0. What is a0? 1. What is b0? 1. So it's going to be 1. Right? Very, very good. So now n is greater than or equal to 1. Cn. I equals 0, n, an, b, n minus I. Let's try to compute this. Actually, this is the same as this, right? Oh, this is I. N minus I, bi, right? These are just the same. They represent the same sum. And what do we know about bi? What happens if I is greater than or equal to 2? 0. It's going to be 0. So even though we may have more terms, they are all going to be 0, except I equals 0 and I equals 1. So I equals 0, we have a n b0. Let's expand this for. So we have to have expansion like this up to a0bn, right? But these are all zeros. Is that right? Because over here. But now what? What is an? 1. b0, 1. a1, I minus 1 is always 1. What is b1? Minus 1. So 1 minus 1 equals 0. So we have just proved that Cn is 0 if Cn is greater than or equal to 1. Right? So this means, although this may look like infinite series, we have just proved that this is 1 and these are all 0. So it's going to be 1. So this is a very formal proof that this multiplication of these two is equal to 1. Any question? But usually the way I multiply two generating functions, let me explain one more time how we multiply these two. if you want to multiply these two, you just choose one term over here and one term over here, and then you just multiply them together. So if you choose here and here, then what do you get? There are infinitely many ways to choose one here, one here. So that's why we get a series instead of a polynomial. This will be computed like a1, b2, x cubed, something like that. So whenever you have x to the n, you will have a something, b something, but their subscripts must add to n, because that's the way these are constructed. So it's always, there are many different ways to select this, but if you have this, and if you have chosen ai, the other coefficient here must be this. That's why we get, there are many different ways, but eventually, if you collect these together, then you will get something like this. So this is very natural definition. So when you multiply two generating function, just select one term, and multiply them. This is how we multiply two polynomials, and this generalizes nicely to formal power series. This is all we need to do, basically. Question? All right, so there are many, or not very many, but this, you can prove this. You can use this fact later. So inverse of inverse is itself. You can prove this using just the definition. So I'm not going to prove this here. All right. Okay, I think I forgot to mention very important thing. I said not every formal power series has the inverse. So, but there is actually very simple criterion for a polynomial, for a formal power series to have the inverse. F of x has the inverse if and only if okay, let's say this way, this is not 0. Okay, I didn't define this, but this notation, this is just notation. Suppose that f of x is f0, f1, x, f2, x squared plus ... Then this is called f0 is called the constant term, and sometimes denoted just f of 0. In fact, it's called formal power series, or also called generating function, but it's not a function. We will not regard this as a function. So what is a function? F of x. If f of x is a function, we plug in x something in x, and f of x will give us some value. But this is not the case in generating function. We will not consider this as a function. It is considered as a function in analysis, but we have to worry about the radius of convergence, something like that. But in combinatorics, in my course, we will just think of this as a formal power series, not a function. So we will never, not never, but mostly it will be very rare that we plug in x equals something, except x equals 0. X equals 0, you can think, oh yeah, they are all 0, so we get f0, f sub 0.
So then, can we apply the evaluation homomorphism instead?
Evaluation of what?
Evaluation homomorphism, which plugs in something.
Oh, evaluation homomorphism. we will plug in x equals 0 only if we plug in anything. Yeah, so in that case, I think it's fine. But instead of plugging in thinking of this as x equals 0, just think of this as a definition. Yeah, for now, I will just say this is just a definition or common notation for this constant term. Because x equals 0, we can always plug in x equals 0 because they will always converge. So this means the constant term is non-zero. As long as the constant term is non-zero, it has the inverse. Proof exercise. But use this. It is related to this. We know that it has inverse. I mean, 1 minus x has inverse. If a formal power series has non-zero constant term, you can find its inverse using the argument as we did over here. But yeah, it's an exercise. Right. Okay. Example. I'm going to show you a perfectly valid series in calculus or analysis, which is not a valid formal power series. For instance, this x plus 1 n over n factorial. Yeah, in calculus, we know that this is e to the 1 plus x, right? This has radius of convergence infinity, so you can plug in anything in x. X can be anything, and it will converge. So it is perfectly fine in calculus, but this is not a formal power series. We will not consider a series like this because formal power series, this is analytically okay. Okay, but not a formal power series. So why? By formal power series, I mean we have to compute the coefficient of x to the n in finite time, in finite sum. We don't want to consider infinite sum. Although, I wrote this as an infinite sum, but we don't really sum this. It's just an expression. But whenever you want to compute the coefficient of x to the n, that should be done in a finite step. So for instance, constant term is what? Constant term means like this, no x in it. So here, in order to get constant term, or you can plug in x equals 0, that gives you the same thing. Constant term is this, okay? But we know for sure that, this is E. But this step is not formal. It's not a formal power series. We don't add something, non-zero things, infinitely many times. This is not what we do. So when we have something like this, infinite sum involved for non-zero terms, that's not going to be formal. In formal power series, so very important, in formal power series, an, or coefficient of xn, should be, this must be computed how can I say, in finite time, I don't know, as a finite sum, not an infinite sum, not like this. because all we can do is to add two numbers together. If you can add two things, you can add three things, you can add four things, you can add 100 things, you can add n things for finite n, but not infinite things. Any question? All right. Now I'm going to talk about limits of formal power series. Yeah, we do have limits, definition of limit. So f of x, formal power series. Also, yeah, let me write this as a formal power series like this. Yeah, then Fn is called, I just use this without definition, but you will probably understand this, called the coefficient of x to the n in F. And this is denoted like this, bracket x to the n f, or f of x. This means we compute the coefficient of x to the n, or yeah, the number multiplied to x to the n in the formal power series expansion. And the degree of f of x is, in polynomial, usually the degree means the highest, the largest integer n, such that the coefficient of x to the n is non-zero, right? That is usually the definition of the degree of a polynomial. But for formal power series, if you define degree like that, most formal power series will have degree infinity. So we define this in the other way. This is the smallest d, such that the coefficient of x to the d is non-zero. Okay? Then degree of this, we have some properties like minimum of degree of f, degree of g, we have this property. And degree of f times g is equal to degree of f plus degree of g. All right? Maybe some example. What is the degree of x cubed plus x to the fourth plus da da da? That's 3. The smallest d such that the coefficient is non-zero is 3. What is the degree of 1 plus x? 0. 0. Degree of 1? 0. Degree of 0? Yes. Yeah, in this definition it should be infinity. Or does not exist, I don't know. Yeah. Yesterday, this is just a definition. Just define this to be 0. Infinity. Alright, so now we have defined coefficient and degree. Now the definition for limit. Definition. So we have a sequence of formal power series. The sequence of formal power series. Formal power series. What is the limit? They define the limit n goes to infinity f sub n x equals fx. If the following is true. for every n, there is n, capital N, such that x to the n, the coefficient of x to the n of f of x is equal to the coefficient of x to the n f I of x for all I greater than capital N. So if you remember the definition of the limit in calculus using epsilon delta argument, this is an analog of that. So what it basically means is that the coefficient, if you look at each coefficient, it will eventually become stable. We have infinite sequence of formal power series. They can be very different. But if you look at just say x to the fourth, then you look at the coefficient of x to the fourth in every formal power series in the sequence. It can be different in the first few terms, but eventually it will become the same at some point. Must be the same at some point for every integer n. This may not exist. If it exists, we say that this sequence has the limit, and the limit is f of x. Actually, there is a very simple criterion for this limit to be exist. I greater than or equal to 0. Oh, well. So this is infinite series of formal power series. This may not exist, but this converges. Converges means it has the limit if and only if limit n goes to infinity, degree of f of n is infinity. Oh yeah, maybe if you just look at this definition, maybe a little confused, but basically what it means is that in terms of this summation, this basically means converges intuitively. Let me say this intuitively. This converges if and only if we can compute. Converges means it is a valid formal power series. Valid formal power series means x to the n, the coefficient of x to the n must be computed in as a finite sum. We can compute the coefficient of x to the n as a finite sum. So whenever we have infinite sum or infinite product, we have to check if this is a valid formal power series or not. Because sometimes it may not be a valid formal power series. For instance, like this. This is not a valid formal power series. Cannot be computed in as a finite sum. So let me give you some examples that will be helpful. So always remember this. This is the important part. Formal power series. This is the essence of the formal power series. Finite x to the n, coefficient of x to the n can be computed as a finite sum, not an infinite sum. Okay, let me give you some examples. I greater than or equal to 1, 1 plus x to the I. What does this mean? In fact, this is not exactly in the form of the formal power series, right? So this is, right now we don't really know whether this is indeed the formal power series or not, right? This means what? Limit. Actually, it means limit. N goes to infinity. Product I from 1 to n, 1 plus xi. This means this. So now what is this? Is this a formal power series for every n? Yes, it is even a polynomial. So it is a formal power series. So it's basically this is the limit of a formal power series. This is just shorthand for this. We just use this because it takes more time to write limit here. So right now, we don't know whether this converges or not. But it does converge. Why? We can compute x to the n in finite time. This is a valid formal power series, meaning it converges. It converges. Why? In order to check, you can this is a valid formal power series. All you need to do is to compute this, is to see whether you can compute this. So suppose you want to compute the coefficient of x to the n for a fixed n, say like 100. How can you compute this? If you have to look at infinitely many times, then it's not going to be formal. Do you have to look at infinitely many factors here? No, you don't have to. Because, why? That's right. So let's divide this into two parts. This is surely true. Say j is n plus 1 to infinity, 1 plus x to the j. This is true, right? I just rewrote this way. But now, this is not really essential in computing this. Here, you don't have to, you have to choose only one. Whenever you choose this, so basically when we multiply products of polynomials or formal power series, we choose one term in each factor. So you choose one term here, one term here for each factor, right? So basically we have infinitely many choices. But the thing is, in order to get x to the n, even though it look like infinitely many choices, we only need to look at just finite terms. Because here we have to choose one only. Whenever you choose this, it will be already bigger than x to the n. So you have to choose only this. Now, that means this is basically equal to this, the same as this. Because we don't really need this term. Because it's just one, the same. But now, you are choosing x to the n, coefficient of x to the n in a polynomial, which is finite. So it's finite sum. It can be computed in a finite step. So it is okay. So this is a valid formal power series. Now, what about this? I plus x to the I. Or, yeah, okay. Let's use a different notation, different example, simpler. 1 plus xi. Is this a formal power series? How many of you think that this is a formal power series? Raise your hand if you think this is a formal power series. Raise your hand if you think this is not a formal power series. Okay? Yeah, more students think that this is not. Why? Just imagine the coefficient of this. Just say you want to compute this. Can you compute this in finite time? Or in other words, do we have to look at every factor? Yes, we have to look at every factor because every factor has possibility to contribute to this, except one, because it has x. So for instance, let's say just x. Xn equals 1. Just look at this. Even for this, suppose you want to compute x, coefficient of x. So basically it is like this, plus 1, 1 plus x, 1 plus x squared. Oh yeah, actually it's not there. I is from 0, 1. So. X, you can choose x here and 1s elsewhere, or here, or 1s for elsewhere, etc. There are infinitely many ways to select x to obtain x here. So it's not a formal power series. You have to understand the difference between these two. Is this clear? It's they are different. This is okay, but this is not okay. So we will not consider something like this. We will only consider formal power series like this. All right, let's go back and move on to another operation, composition. So for two functions, we can compose two functions, and we can do the similar thing for a formal power series: f of x, g of x, formal power series, and we assume that the constant term of g is 0. F g of x is this. Of course, f of x, summation xn. So xn means the coefficient of x to the n in this formal power series and this. All right. Now, this is again infinite sum. You have to check whether this is a formal power series or not. It is formal power series, provided that the constant term is 0. This is important because otherwise this is not going to be a formal power series. Example. Okay. Let's just see. This is in fact composition of two functions. Where g of x equals 1 over 1 minus x. You just replace x by the things inside. And this is this. If constant term is non-zero. So why? So why is this important? Let's consider this. Again, let's say g of x equals 1 over 1 minus x, or 1 plus x squared, And let's say a of x equals 1 plus x. Very simple. And try to compute g of a of x. What is this? You just plug in, you just substitute x by 1 plus x. 1 plus x, 1 plus x squared, 1 plus x cubed. This is not a formal power series. You cannot compute the constant term in finite time because every term has constant term, non-zero constant term. So if you want to get constant term or the whole constant term, you have to add infinitely many times. So it's not a formal power series. So that's why this is important. All right. There are more operations in formal power series. You can even do calculus, formal derivatives. So f of x is equal to this. Then this is the definition. The derivative of f of x denoted this, or like calculus, we may use different notation for this. They may mean the same thing. And this is the definition. And from this is the definition. Or you can say from 1. So in calculus, when you take the derivative, we take, if it is a sum of many things, we take the derivative of each term and then we add the result. That's the property of derivative. And for this, so when you take the derivative of a sum, you just do this term by term. And when you do derivative of a monomial like this, derivative of x to the n is n times x to the n minus 1. That's the same. But this is just a definition. This is not a corollary of something. It's a definition, formal definition. If you shift the index by 1, you can also write this as this. Then, using only these formal definitions, you can prove the derivative rules like this. And product rule or Leibniz rule, these can all be proved using just the definition. Chain rule using formal definition. Any question about this? I'm not going to prove this. It's an exercise. So because of this, these are comparable with the usual properties or definition in calculus. You can use things from calculus because they are satisfied also in this formal language. This is the useful features of generating function. You can use these kind of many useful properties. Okay, some useful generating functions. This is another definition. E to the x or exp of x. This is defined to be this. This is a formal power series. This is useful because it has nice properties. And log of 1 plus x is by definition n from 1 x to the or minus x to the n. Or if you want, this is this looks nicer in this formal power series, but they are equivalent. And A is indeterminate, or just any number, or just you can think of this as any number, complex number, or indeterminate or variable, then this is a definition. Where this binomial coefficient is defined to be this polynomial. And this is comparable with the definition of the original binomial coefficient. When n is an integer, positive integer, this is equal to just the usual binomial coefficient. And you see here, alpha can be anything because this is a polynomial in alpha. You can compute this for any alpha, not just for integer. So power function can be defined in this way. And we have many properties of this. 1 plus x to the alpha, 1 plus x to the beta. This is equal to 1 plus x to the alpha plus beta. So this is comparable with the usual power function. You have to remember that this is not a trivial thing. If you know what I mean? This is not a trivial thing. It follows from the definition. If you confuse this with the original power function, you may think, oh yeah, this is trivial. Why do we have to prove this? But this is not. This follows from this. Try to prove this. We know that exponential functions and logarithmic functions are inverse of each other. That can be proved in this way. No, just x. They are inverse to each other in this sense. You may wonder why we have 1 plus x instead of x. Because we want this to be a formal power series. Yeah. So for logarithmic function, we must have a constant, non-zero constant term. This has non-zero constant term. This is okay. And some more. E to the x, e to the y, e to the x plus y. Also true. E to the x raised to y, e to xy. By the way, what does this mean? What do you think this means? We know this is okay. This is okay. We can multiply them. This is okay because e to the x plus y, I think this is okay. But what about this? This should be understood as follows. This is in fact, because this is a power function, we have to convert this in this form. How? 1 plus e to the x minus 1 y, right? So it is now 1 plus something. So this is in fact, so this 1 plus x raised to y, it says this is in fact a composition of two functions. So so you have to understand this that way. So in that way you can prove this. Okay, there are more identities to go. 6. 1 plus x raised to alpha e to the alpha log 1 plus x. So many things that we already know in calculus can be proved formally. 7 log 1 plus x raised to alpha equals alpha times log 1 plus x. 8. Derivative of the exponential function is itself. And derivative of the logarithmic function is, we know, is 1 over 1 plus x. They can all be proved using d dx alpha. They all can be proved. Yeah, there are many things. So for now, you know the formal power series and their operations. When you have any your favorite property of in calculus, you can try to prove this formally. It should be possible if it's true. Okay, any questions so far?
Professor,
Yeah.
there are many properties in these power series, but can we prove it combinatorically besides that algebraic?
Oh yeah, they will all, they can be proved combinatorially or formally. Yeah. All we need, so we have all the ingredients to prove this, just the definition. And by definition and the way we multiply two things. So basically these are all combinatorial problems in that sense. Because when we multiply two things, you select one term in each vector and then you do something. So these can be proved formally or combinatorially without using calculus at all. You don't need calculus. Other questions? Okay. Now let me show you one example of finding how. One example I'm going to show you. Suppose we have a sequence given by this recurrence relation. Or I think it's 0. For every n, it's defined with this. So an is defined, is well defined. By using the initial condition and the recurrence relation, you can compute a1, a2, etc. always. So it is a uniquely defined sequence. We want to compute the nth term. Okay? Let's do this using generating function. So solution. Let's say a of x equals this. So generating function for this. Okay? And what is this? This, you have seen this before. When you multiply two generating function, it looks like this. So a of x times a of x is equal to, by definition, I from 0 to n, a n minus I, x to the I, n. But this is defined to be equal to 1 always, so it's 1. This is geometric series, so it's 1 over 1 minus x. Because this is always 1. All right, now, yeah. So, what now? A x squared equals 1 over 1 minus x. What is this? Inverse. From this, actually, we can say a of x is equal to 1 minus x minus 1 over 2. Yeah. Here, I used many properties that are true in generating function, formal power series. I omitted some things, but yeah, things like this. You need things like this. Okay? Maybe you can take, you may need to take logarithm or something, but you can do, you can apply the things that we use in usual calculus over here. So this can be divided. You can by 1, and this can be divided by 1. Now, this is a form of 1 plus x to the something. So you can use the definition or definition of 1 plus x to the alpha. So it is going to be equal to minus 1 over 2 alpha minus 1 to the n x to the n. Oh, this should be n. Okay? Now, from this, you can expand this using the definition of the binomial coefficient. And if you do that, you can compute this is equal to, an is equal to minus 1 to the n minus 1 over 2n. This is going to be equal to 1 over 4 to the n, 2n choose n. You can compute things like this. So sometimes you can use generating functions to find the formula of a sequence given by recurrence relation. Okay. Now we will take a, say, 10-minute break and then resume after that.